Welcome to this lecture on algorithm analysis and its introduction. Today, we're going to start a longer discussion on motivating what's known as algorithm analysis. And we're going to talk about some questions for thought and talk about a loose framework of what an algorithm is, but we'll delve into more details in later lectures. So here are some questions just to get the ball rolling. And you might write these down. You might pause and write these down. How could we estimate the time required for a program to run? You might use a stopwatch, right? You could say go and then you hit your stopwatch, and then when it finishes, you press stop. But how general is that? How general is that from a standpoint of what if the algorithm runs really quickly and you don't have time to even push the button? Or what if it takes days or years to run? It's not really going to be that useful for us. Another question, which is just to get to jog our thinking about this, is if we have a program and it's already implemented, or at least we've designed it, and we know that it's going to be too slow, how could we speed it up? Well, a good rule of thumb is to identify what is the slowest part of our program and work on that. But how do you identify which part is the slowest? Algorithm analysis can tell us a lot about that. Here are some more questions for thought. Suppose that you have a really important task, like you want to write a program that solves making a menu, a dinner menu, for a dinner party with N people, okay? So you're making a menu, and that's the task, and you have N people. And the more people, of course, that you have, maybe the more options you want to give, and maybe the more constraints you also have, because people might have constraints in what they can and cannot eat. So maybe it gets more complicated as you have more people. If it takes 30 seconds to make a plan for 10 people, how long does it take to plan for 20 people? If it takes 30 seconds for 10 people, how long does it take to plan for 20 people? Well, your immediate reaction might be, well, it takes 60 seconds, right? Because you double the number of people, you double the amount of time. But what if the amount of time goes up by a factor of 10? So it goes up from, you double the number of people, and it goes up from 30 seconds to 300 seconds, or 5 minutes. Is that possible? Yeah, that's possible, because we haven't really talked about how the speed of the algorithm behaves with respect to the number of people. That's what algorithm analysis really addresses. If we have two algorithms, here's another question. If we have two algorithms that both plan menus, but they do it in different ways, could we know which one of them is faster? And could we do that without actually timing them with a stopwatch? Well, algorithm analysis gives us tools to address this question. It tells us which algorithm is faster in general. So here's a third question for thought. If you have two algorithms, again, that do the same thing, such as plan menus, is it possible that of these two algorithms, A and B, one of them is faster at planning a menu for a small party with a small number of people, small n, and the other one is actually faster for a big party with more people, bigger n? Is this possible? Yes, it's possible, and it can happen all the time. The fourth question is even more general. Is it possible that there are what I would call algorithmic speed limits? Speed limits meaning no algorithm can go faster than this rate for some task. So, for example, if the task is sorting numbers, we're going to look at this later in the semester, is it possible to prove that there is a speed limit and no algorithm can go any faster than this speed limit? And it's theoretically provable that that's the case. Okay, we'll answer that later, but this is just to get your thinking going about this. The framework that we're talking about for algorithm analysis is a formal framework. It's a mathematical framework for measuring and comparing the performance of different algorithms. And the nice thing about our framework is that we can compare the efficiency of different algorithms without timing them, without using a stopwatch, and often without even implementing them. And that's a good thing, because computer technology changes quickly. We can talk about the speed of an algorithm without reference to the speed of an algorithm on this computer versus that computer. Just how fast is this algorithm, not how fast is this algorithm on this computer at this time. And we'll talk more about the exact tools that we'll use in a later lecture for doing this formal analysis. But for now, I'm going to finish with this. Let's define what we mean when we say algorithm. An algorithm is a set of instructions which, if followed, accomplish a particular task. And it has a few key attributes. Every algorithm has some input, has output, and it is definite. When we say it's definite, we mean that all the parts are defined. There's no point at which we say, wave your hands and something magical occurs. No, every part is well defined. It's also finite, which means we can describe it concisely. We can write all the parts down. An algorithm is not an algorithm if it would take us forever to write it down. Okay, this doesn't actually have to do with whether it will finish running. It has to do with whether we can write down what all the steps are. And it operates on data. Now, this last step, along with the input and output, might seem obvious, but these are the components of what makes an algorithm, the formal definition. Come back and we'll start talking about the formal framework that we'll use to actually do the analysis of these algorithms.